When we are looking at force problems, they will not always be as simple as the one that we did in the previous lecture, where all the forces are either up and down or left and right. Same thing down here. All the forces were either up and down or left and right. That's a pretty simplistic view of the world. We certainly do not operate only up, down, or left and right. A lot of the times we have problems where perhaps we are pulling something at some kind of an angle, like this exercise here. This is a box where it is attached to two ropes. One rope is here, it's pulling 25 degrees left of vertical, and then we have another rope here that's pulling to the right. Now, we would like to be able to solve problems like this, but we run into an issue in that we currently only can look at forces that are either left and right or forces that are up and down, and not this kind of in-between force. Now this force is pulling both up and to the left. So what we need to do is we need to figure out exactly how much of this force is pulling to the left, and we need to figure exactly how much force is pulling up in order to be able to use those force equations that we went over last time. So how are we going to do this? Well, it's exactly like what you see right here. We're going to be creating a lot of right triangles. So before we start to try to do exercise 3, let's do a little bit of a refresher about right triangles. And hopefully this will just be a total review of your geometry class and it'll be a breeze. But really fast, let's talk about the parts of a triangle. Now, a triangle always has 3 sides. The longest side is referred to as the hypotenuse. Now, one of the things about a triangle is that we need to know one of the angles most of the time. And we can find any other side of the triangle based on the hypotenuse and one of those angles. So the side of the triangle that is opposite of the angle is called the opposite side, and then the side that is right next to the angle that we know is called the adjacent side. And so as long as we know 2 out of these 4 things, we can find out all other parts of a triangle by using these proportionalities called trigonometric functions. So the first trigonometric function is sine. So if you take the sine of an angle, that will tell you the ratio of the opposite side of the triangle divided by the hypotenuse of the triangle. Cosine is another trigonometric function where if you take the cosine of an angle, it tells you the ratio of the adjacent side of the triangle divided by the hypotenuse of the triangle. And sometimes you don't know anything about the hypotenuse, and so that's why we have tangent, because tangent of an angle will tell you the ratio between the opposite side of the triangle and the adjacent side of the triangle. Now we will be using these 3 trigonometric functions as well as their inverses for the rest of this class, first semester and second semester. The other thing that we will be using all the time is Pythagorean Theorem. So remember that the hypotenuse squared is equal to the opposite side squared plus the adjacent side squared. That one is always a handy one to have in our tool belt as well. Now, we will not always be referring to these as the opposite and adjacent side in this class. In fact, most of the time, the legs of the triangle are going to be referred to as the x component and the y component. So an x component is trying to describe the amount of something in the x direction. And the y component is trying to describe the amount of something in the y direction. I say the amount of something because x component and y component can refer to anything. We could try to find the x component of displacement. We could try to find the x component of velocity. And in this unit, because we're so focused on forces, we will probably be trying to find the x component of a force. So let's do a quick example where you find the x component and the y component of the given force. So this first one is a 12 Newton force that is at 60 degrees. And so what I want to do is I want to make a right triangle out of that. And then I have my x component and my y component. If I wanted to find that x component, I see that that x component is the adjacent side to the 60 degrees, so I'm going to use cosine. I know that cosine of 60 degrees must be equal to my x component divided by 12 newtons. So I can multiply 12 to the other side. 12 cosine of 60 will tell me my x component. It must be 6 newtons. That is my x component. For my y component, that is the opposite side of my angle. So I'm going to use sine. So I've got that sine of 60 is equal to y divided by 12 newtons. And so 12 times the sine of 60 will give me my y component. And so that is approximately 10.4 newtons as my y component. For good measure, let's do another one. So here's a 15 Newton force at 20 degrees above left, I suppose. And I need to make this into a right triangle. So let's draw down and then across. So we see the right triangle. We can see that this must be my x and this must be my y. So again, my x component is the adjacent side of my triangle. So, oops, sorry, I got to start with cosine of 20 is equal to x divided by 15 newtons. So 15 cosine of 20 will tell me what my x component is, and that ends up being 14.1 newtons as the x component. Now this is in the negative direction, so I'm actually going to add a negative sign to that, because we always want to be aware of what direction we're moving in. These are vectors after all. Then for the y component, that is the opposite side from my 20 degrees, so I'm going to use sine of 20 is equal to y divided by 15 newtons. So 15 newtons times the sine of 20 will give me y. And we end up with 5.13 newtons as our y component. And that one is positive because it looks like that y is going up. Okay, so that's a nice review of geometry. We now can use that geometry as well as our knowledge of force equations in order to finally be able to solve problems like exercise 3. So, using the picture to the right, answer the following questions. Write the equation of the forces in the x direction. Part B, we will write the equation that describes the forces in the y direction, and then in part C, we will find the tension in the two cables. So the first thing that I want to do is I want to draw the force diagram for this box. I'm actually going to draw it away from the box so that I have a little bit more room. So we'll pretend like this is our box. And I know that this box has a force of gravity on it, on the box by the earth. Now we've got one rope that's pulling us kind of up and to the left. And I'm actually just going to call this T1, T for tension. It'll make it a little bit easier to write than FT1 or FT2. Anyway, this T1 is pulling on the box by the rope. And then we've got this other rope that's pulling us to the right. We're going to call that T2. And it's on the box by a different rope. Okay. Now, we see that T2 is pulling us to the left and T1 is pulling us to the right. How much is T1 pulling us to the right? Well, what we can do is we can create a nice little right triangle to help us see how much T1 is pulling to the right. So this is 25 degrees right there. They told us that in the problem. And if I write my net force equation for the x direction, we already said T2 is pulling to the right. And then we want to try and describe this one part of T1. It's just the part that's pulling us to the left. So I'm really trying to describe the opposite side of my triangle. So the opposite side of my triangle could be written as T1, which is the hypotenuse, times the sine of my angle. That's going to describe that highlighted part of the triangle. And those two things are going to need to add together to be 0. If I sum the forces in the y direction, I've got force of gravity pulling me down. And then there's the part of T1 that's pulling me down. So we're really talking about this part right here in the green highlighter. That part is pulling me up. So how can I describe that part of my triangle? Well, that part of my triangle is adjacent to the angle that I know. So I would use cosine in order to help me describe that part of the triangle. Now I want to find the tension in the two cables, and these two force equations will help me do that. Because I really only know one thing. I just know this 100 newtons, and that's the force of gravity on the box. So we know that this Fg is 100 newtons. And since it's down, we would even say it's negative 100 newtons. So I know what this number is in my net force equation for the y. And if I look, that means the only thing I don't know would be T1. So I could probably use this equation to help me solve for T1. So I've got negative 100 newtons as my Fg, plus T1 times the cosine of 25 degrees. That has to add together to be 0. So we add 100 newtons to the other side. We got T1 cosine of 25 has to equal 100 newtons. We divide both sides by cosine of 25. So T1 equals 100 newtons divided by the cosine 25, and we end up that T1 is about 110 newtons. And now that I know T1, I can totally find T2. So let's use our force equation for the x direction to find T2. We got T2 plus, and since this is pointed to the left, I'm going to call it negative 110 newtons times the sine of 25 degrees has to add together to be 0. And when we do the algebra there, we find out that T2 is 46.6 newtons. Now notice that this is the exact same problem-solving process that we did with Ruby and the car that was in the snowdrift, where we drew a force diagram, right? That was step 1. We wrote some force equations, that was step 2, and then we used those force equations to solve what we were interested in. That was step 3. It is the exact same problem-solving process that we'd used before. This is just slightly more complicated because we had to find the components of one of our forces in order for us to be able to solve the problem. But that's not a big deal because the process was still the same.